start a session about data. So we talked a lot about models, methods, algorithms, applications and stuff, but if you ask me, the most important component of all of this is data. And we are excited to have Hynek with us, who will present probably the most important open source data set for LLM training. And he will present how they have built this. So please, let's start.
Yeah, so thank you very much for the introduction. As was said, today we'll be talking about FineWeb 2, which is the dataset which we built last year. And it's a large pre-training multilingual dataset, which contains only text, and contains actually about 1,700 language script pairs. So like the language coverage is very, very big. So before I even start talking about how we kind of approach the dataset building and how we actually build the dataset, it's important to talk about why we even decided to build the multilingual dataset. So as is from the name, you can kind of tell that this is not our first dataset we built. This is not the first FineWeb. Actually, this is the second FineWeb. And the first FineWeb dataset that we built is FineWeb 1. And on FineWeb 1, we really learned like how to kind of approach this data refinement process. And when we finished, we were wondering what we can do next. And we kind of look around, and one area that I still think is like super heavily underinvested and underexplored is the multilingual stuff. Like, for some reason, people don't seem to really like the multilingual stuff, so we really thought we could help and help in this domain quite a lot. And one thing we also thought is that this is gonna be like super fast project. We're just gonna take our pipeline from FineWeb 1, we're just gonna adjust some stuff so it works on the other languages, and we will be done in like 1 month. Well, this was the biggest lie we ever told to ourselves, because we spent about 6 months, and the reason is that the languages are like super different. We never thought the languages can be like super different from each other, and so this will be kind of a journey like about what we found and how much the languages differ. Okay, so the motivation is done. So before we start talking about why we built the data set the way we did, it's important to kind of talk about the data quality, because that's your ultimate goal, to build a data set that's like good quality. But what the data quality actually means. So some people think that they just look at the few samples, they somehow judge how good they are, and then judge the whole data set based on these few samples. But this doesn't work, because like the data set is 1 billion samples in total, and you can't just judge the data set from a few samples you've seen. And more importantly, and quite counterintuitively, humans are like super bad at judging what will be good for LLM training. The second thing that people kind of try to measure the dataset quality with is like gold standard perplexity. People will take some resource that they consider high quality, which many people consider Wikipedia, for example, and then they will train an Ngram model on this dataset and then use this Ngram model on their own data. And if they have a low perplexity, it means that it's like very similar to the Wikipedia, and those have this high quality kind of properties. But it's again not a great measure, because first of all, Wikipedia, while I would also consider it being high quality, does not contain all the stuff you want your language model to know about. So you introduce like a lot of biases. So for example, some words that are like not in proper English will very likely not appear in Wikipedia. And once your sample contains these words, the perplexity will just skyrocket, and you will just remove this sample. So we don't want to introduce these biases. And so the last way people measure data quality, and this is what we actually do, is, well, we want to create high quality pre-training corpora for training LLMs. So let's just measure it for the purpose we want the data set to use. So what we do is that we train a small model on this data set for, let's say, like 30 billion tokens, and then look at the performance of this data set when we train on this, look at the performance of the small model, which we trained on the data set. And if the performance is good for this size, we would kind of call this data set a good quality. And so this is this kind of approach we use throughout the whole data set refining. So whenever we make any data intervention, we train a model pre-data intervention in the completely same setting. So we use the same number of parameters, completely same model for same amount of tokens on pre-intervention data, and then train another model on the post-intervention data, and then compare the performances of these models, and then we kind of decide whether we do this intervention or not. So before I get to the actual building, I will talk a bit more about these ablations, because at the start we thought we're just going to take the English setup, we're going to make some small adjustments, and we can run our ablations. But for multilingual stuff, it doesn't really work this way. So first question is like, before we were doing these ablations just for English, but for multilingual setting, how should we approach it? Should we train one model for all these languages? Should we train many models for many models on each of these languages? Or like, how should we approach this kind of, we really want a good data set that works on your median language? So this was the first question we kind of had to answer. The second issue is that, again, in FineWeb 1, we use some tokenizer for English. Most of the tokenizers just work for English, and there is like no need to worry. But for multilingual domain, once you kind of start playing with the off-the-shelf tokenizer, you will find out that some are just terrible for certain languages. And the last thing is what task we should measure the performance on. So as I said, we are training some small models, and then we use some standardized benchmarks to measure the performance of the model. But the issue is that for English, again, you just go see the papers, you use a lot of standard tasks like MMLU, HelloSpec, you just have like, you just have so many tasks you can choose from. But for multilingual domain, you have the tasks scattered all over the internet. There is like not really a standard set that you should use for these kind of languages, and it's like really mess. So we really had to answer these three questions. So for this first question, whether we should train one big multilingual model and then judge its performance, or we should train multiple models on many languages, we decided to go with the second. And the reason is that if we would train one multilingual language and then judge its performance, we would introduce like big confounding factor, which is we would have to decide how many tokens we will allocate for each language. And this could change based on our filtering or like processing measures. So let's say we, for some reason, had a lot of tasks for Arabic, and one of our data step would remove a lot of data for Arabic. It would very likely influence the performance a lot because, I mean, we would not train on this many Arabic tokens. So we did not want to introduce this confounding factor. And so we decided to use 9 canary languages, which we chose so that they are like very diverse. This means in the script, in the language family coverage, and on like the resource availability. This means that like we want very high resource languages and the low resource as well. And so these are the 9 languages we choose. Unfortunately, no Armenian, so we hope it still works for that language, but it was not the one we kind of tracked. So this is the languages. Then we had to choose the tokenizer. As I said, problem with tokenizers is they are good on English always, but for some languages they are like super bad. And so for measuring the tokenizer performance, you can kind of use 2 metrics. One is sub-word fertility, which tells you how many tokens do I get per average word. So if it's 2, this means that average word will every word will more or less on average create 2 tokens. So you want this metric to be as low as possible to have pretty much 1 token per word. The second metric is very similar, and the idea there is that we measure fraction of the words that we split on more than 1 tokens. So again, you want this metric to be super low so that you don't split your words in half to multiple tokens. And so this is our result. I'm not sure how readable it is, but you can see that for most of the languages, especially high resource, most tokenizer kind of work. But once you get low resource language that is like not supported, like Telugu, your metrics like absolutely explode. So for Telugu, most of these tokenizer will create for one word 10 tokens. So that's just super bad when you consider English, where for one word you will get something like 1.445 tokens. So yeah, it's like super bad. And so we kind of ended up with choosing between the tokenizer that was used for Big Science Bloom. This is a model actually made by HuggingFace, and the Gemma model that's made by Google. And we ended up going with Gemma because it had a bit better metrics I was talking about before. There are 3 tokenizers that we decided not even consider at the end. MT5 and XGLM we decided to throw out because both of them use, they are kind of all tokenizers. And when they see out of dictionary word, they will just replace it with unknown symbol, which is kind of cheating because all the other tokenizers will have to use 1 token per byte if they don't know this, have never seen this word. So it's kind of cheating. And the Cohere ML we decided to not use because it's just too big tokenizer. And if we would use this tokenizer, it would kind of mean that we would just have the embedding layer and 1 layer for the transformer. So it would literally just be pretty much embedding layer and nothing else. So this is the final setup we decided to go with. It's 1.46B parameters. So as I said, small model. And now last thing, before we get to the actual dataset building, is the tasks that we're gonna measure the performance with. And this is like super important thing to spend your time on because the task selection will heavily influence the way you kind of filter data because we filtered the data so we have a good benchmark. So you really want to think about what benchmarks you want to track so that your data are reflective of these benchmarks. So as I said, multilingual benchmarks are very hard to get. And big problem with them is that many of them are actually just a translation of English tasks using machine learning translations, usually not even humans. So they are not super high quality. And so as I said, you really want to spend time with kind of thinking of how you choose these benchmark sets. And so we decided that we want our small models to focus on kind of 4 capabilities we defined. So first is the reading comprehension, which is literally a task where you get a paragraph of text, and your goal is to extract some information from it. So I give you a paragraph, and then I ask who said this phrase. Your goal is to answer this question, who said this phrase in the paragraph. The general knowledge is just like retrieving knowledge from the model. So I'm sure many of you know MMLU benchmark. So this is exactly this kind of task. So the question can be like, who was the president of the United States in this and this year? Then there is a natural language understanding, which kind of like tracks how model can actually understand the language. So if I have a phrase, he is very smart, and I give a model to completion to choose from. One is, therefore he could be a good university professor, or the second completion could be, therefore he is super dumb, which makes no sense. The model should choose the professor completion because it's clearly more like it, and kind of show that the model can understand the language. And the last one is common sense reasoning, which is very similar to the natural language understanding, but here we kind of require the model to understand to have some word model of the word. So again, if there is a prompt with the ball fell on the ground, and I give it 2 completion, one is then the ball started talking like an animal, and the second completion, it bounced back to my hand. Again, the model should choose the option with it bounced back to my hand because it kind of understands what the ball should do when I throw it on the ground. So these were like capabilities we wanted to track on the model. And the last very important thing is that all the benchmarks we evaluating using something called log probabilities accuracy, which means that you give the prompt to the model, and then you give it 4 completions, and then you choose the completion that has the highest probability of generating, which works, but the problem is that it's not a generative task. You are just kind of discriminating out of these 4 options that you are giving to the model. And so what can really easily happen is that you will have a model that can very well understand the French or whatever, but it's not able to generate the French at all. It's like super bad at it. It's only good at discriminating between these 4 options we always give the model to. And so one requirement and last one we had is that we wanted to have, for every language, we want to have this generative task. And yeah, that's it. Even though it doesn't solve the problem that much, because the generative tasks we have usually mean they have to generate like 4 or 5 words. So it's like not nice phrase generation. And the reason why we don't have nice generative tasks is because evaluating overall fluency of the model is like super hard task, and we honestly have no idea how to do it in a non-biased manner. So if somebody is exploring this direction, I would be happy to talk to you. Okay, so this is the capabilities wanted, and I will kind of skip this part because it's not super important. But then we kind of gathered all the available tasks that we found on the internet. We got around 1,000 tasks, and using some kind of smart metrics, what we kind of expect from the tasks to behave when we train on them, we decided to end up with, wait, I can visit. We ended up with 96 benchmark across these 9 languages. And so this was the big preparation. Now we kind of understand how we measure the quality of the data set we will be building. And this means that we can now start actually building the data set itself. And so the first question is like, where do we source this data from? And right now there is only one source that you can gather this data on such large scale, and that is Common Crawl, which is the most crucial resource in NLP by far in the history, I would say. And they have been gathering not all the internet, but like big part of the internet past 20 years. So they have a huge index of all the web pages that existed throughout this time. And so, as I said, this is our second data set. So our idea was that we're gonna exactly replicate the pipeline we did for the for the English section of this one. So as I said, we are starting from the Common Crawl, from which we get all the HTML files that are there. And what we start with is something called URL filtering, which means that there exists like a huge database with all the URLs that are somehow toxic or harmful. This means there is like so many like URLs for the porn sites, there are gambling sites, and all these kind of bad things you don't want your model to not know much about. So this is why we first do URL filtering, because we are able to remove a lot of bad stuff through this very simple and non-costly filtering step. The second step we have to do is to get the text data out of these HTMLs, because as I said, we have HTMLs, and like this is not a great format to train our language model on. And so there are a couple of like open source extraction libraries which will take the HTML and return the nicely formatted text. The goal there is usually to kind of remove the boilerplate, because like most of the website have a lot of navigation bars, footers, headers that have like no value. They are there just for the users so that they can orient on the website itself. So these 2 steps remain the same as in the English FineWeb. And the first step that actually differs, unsurprisingly, is the language filtering. And so the goal of the language filtering is to separate all our text into their correct language bucket. And for this step, we have like many ways we can do this. There are a couple of models you can use. I would say the most popular ones are based on the fast text, which just takes the text, splits it into some sort of subwords, embeds them in some nice vector, and then just puts linear classifier and give you the language and a nice score yeah, the language and the score, how much the model thinks the document is of this language. And as I said, there are like a couple of other methods you can use. The issue is that at this point we have like 200 billion of documents, and you really need something that's like fast, at least like 1,000 documents a second at least. So transformers are not something that you definitely can use. And so for the English FineWeb, the FineWeb 1, we use the FT176, which is the fastest classifier made by Facebook, quite super old, like they made this, I think, in 2012, maybe sooner. And it classifies to 176 languages, and it kind of works okay. But the thing we wanted is that we really wanted to have more languages, and actually found a classifier that not only had more languages, it was also better. And so this classifier is called Glotlit. It was made by one PhD in Munich University, I think. And the nice features of this classifier is, as I said, it supports, I think, 1,700 language script pairs. So it's not just English, you get like English and Latin script. So you get these two parts. And the fact that it can distinguish the language and the script itself is actually helping the performance, because the script identification is like kind of trivial, right? Like you can very clearly tell like what is Latin, what is Cyrillic, what is like the Hebrew script and stuff. But the actual language identification is hard. But the issue is that some languages support like multiple scripts. I'm not sure if I'm correct about this, but I think Serbian maybe has 2 scripts, Cyrillic and Latin, if I'm not mistaken. And so actually identifying these languages which support both scripts can be very confusing when you are training this classifier. And this classifier has distinguishes the script and language, which really helps the performance. And the other like very nice thing about the classifier is that it has the undefined label, which means that if the classifier does not know, it will put it into this bucket, which is great because if you don't have this unknown bucket, you kind of have to decide one language where the classifier will put this language in. And so if you have complete garbage document or something like this, and you train on this subset, it will have to, during the training time, decide to which bucket it should put this document, which again really hurt performance. So yeah, so we decided to try and experiment with this new classifier. But as I said, like we make all this decision by training these small models. So what we did is that we trained the model using the classifier we used before and using our new classifier. And as you can see, for all the high resource languages, when we used the new classifier, the scores were like marginally, I would say, better. But unfortunately, for the lower resource languages, which is, for example, Swahili, Telugu, or Thai, we got a bit of a performance degradation. So we had to make some decision, and we decided to go with Glotlit, mostly because for these high resource languages, we have way more tokens. So we actually care way more for the high resource languages, because like top 50 languages will be like 90% of our whole data set. So it makes sense to make decision based on these high resource languages. And the second thing that you kind of have to decide when you are doing this language filtering is deciding for a threshold of the confidence score. And so as I said, these classifiers, they will give you the most likely language and how confident they are in the fact that the document is of this language. And most people, what they do is that they will just define like one static threshold, and they will just use this for all the languages. And if the confidence is lower than this threshold, they will just throw this document out, which makes sense because some documents that have like very low confidence score, they are usually some kind of trash and not super in-language documents. But the issue with this static approach is that the confidence score and their distribution very much varies based on the language you track this metric on. So for example, for English, this is English like super easy. language to classify because it has just insane amount of data. Your distribution will look something like in the middle. So like everything has pretty much 0 confidence, and like 95% of the data is like super high confidence. But then you have languages that are like that have a very close cousin. For example, Czech and Slovakian are like very similar languages, and thus inherently the confidence score have to be on average lower because the model will oftentimes confuse between these two languages. And on the slides you can actually see the Yoruba, which has exactly this kind of phenomena. So it's not like that most of the confidence would be at 1. The distribution is very different. So therefore you have to be more smart about choosing this threshold. You can't just use the same thing for all the models. And so how do we actually decide this threshold? And we kind of have no idea. So what we decided to do is that we're gonna run a grid search on our 9 languages. So for each language, we kind of found a threshold which would remove 10% of data, 20% of data, 30% of data, and 40% of data. And for all of these thresholds, we trained our small models. And you can see one of the results at the first table. And then based on this kind of grid search, we found like the lowest threshold we can use and the highest threshold we can use, so that these thresholds cover like the best and the second best performance. So on the table, we found that we really want to be like in the range from 0.883, and the max threshold should be 0.9. Because when we trained on the data between this threshold, our model trained on this data was the best. And so we did these 5 ablations for each of these language. So we trained about 45 models. And at the end, we got this nice table where we had the minimum and maximum threshold ranges we are willing to use. And then we kind of had to find a formula that would satisfy all of these ranges. And we should have probably like fitted some simple like linear regression that would take the threshold statistics. So like it would take mean of the threshold distribution, the STD of the threshold distribution, and all these other statistics, and somehow like smartly found this formula. But at the end, what we did is that we kind of heuristically found a nice formula that we ended up using, which is we took like a median confidence score for this language, and we subtracted the standard deviation of the confidence score of our languages. And then we kind of set min and max so that we don't remove too much or too little. So this is how we done the language filtering. And the second stage we had to do is the deduplication, because if you train on the sample multiple times, you're inherently not adding any new information, you're just more or less repeating the data. And there is like clear evidence from many papers that you really want to duplicate, even though how much you duplicate, how much you want to deduplicate kind of depends on your use case, I would say. And so the way we do the duplication is not that we just take 2 documents and check if they are same. We actually do a bit more smart deduplication, which is called fuzzy deduplication. And the whole idea is that I take 2 documents, I look at the words these documents contain, and then I compute the intersection of the words that are same in those documents divided by like total like union of all the words I have in both of these documents. This is a very smart way to do this. The problem with the approach is that if you do it naively and you compare each document to each, you have n² complexity, which you can just never scale because at this stage you still have 100 billion documents. So you would, even if you had like millions of CPUs, they would never finish. So there is like a smarter way to do it. It's called LSH minhash. And I will not talk too much about it because I will just check the time. I think we are okay. Yeah, we have not that much time. So, but yeah, it's just like a smarter way to kind of do exactly this idea, but in linear time. So you don't have to go through this n squared complexity. And so one big issue, which we again did not anticipate, is the fact that for English you can just kind of split on the spaces, and you're still gonna get some reasonable like splitting of on the words. But for some other languages, especially for the Asian languages, for example, Japanese, Chinese, they don't use spaces to separate the words. So you have to use word tokenizers. But the issue is with the word tokenizer is first, like, there are many different libraries you have to support, and each only like supports certain subset of the languages. And more importantly, for some languages, you just have no supported word tokenizer. So we had to kind of find a way to assign the word tokenizers for the languages that just have no official supported word tokenizer. And what we did is that we built like a nice language tree. So you have, for example, Indo-European languages. In there you have like more kind of fine-grained families. And we built this language, and for the languages we had our tokenizers, we could have directly assigned it. And for the languages that did not have any tokenizer, we like devised a very simple algorithm. So we had all these languages with tokenizer assigned, and then based on like their their family. For example, here you have Italo-Dalmatian family. We decided to use the tokenizer which we had assigned and which was from the language which was like the most resourceful. So if we would have in this family, if we would, for example, have Italian and Swahili, we would use Italian because, of course, Italian is more resourceful. And so this way we kind of colored all these circles, as you can see, based on the most resourceful language. And then we done second pass, where we kind of went from the top, and whenever anything didn't have tokenizer, in this case it would be these squares because these don't have official tokenizers, we use the tokenizer of the language that we assigned in the previous step when we were going up to the tree. So this was a very simple idea to kind of find tokenizers for languages that don't have a tokenizer. And so here we can see the effects of the duplication. For most of these languages, these are the languages we tracked, the duplication helped. For some, it just did more or less nothing. And unfortunately, there is like no indication like why this is the case. We kind of try to see if this is because of the languages have, like, for example, super long words or some kind of different aspect, but we didn't find any pattern, so we were just happy with this. And so now we are getting to the, I would say, the most important part, because this is the part that will give you the most performance, and this is the heuristic filters. And so the idea of heuristic filters is you kind of look at the documents and you find some property of documents that is good proxy for the document being either like a good document that you want to keep or like bad document you want to throw out. So like one thing that people usually like to throw out are just like super long list of just like one word, literally just like a list. And this you can easily throw out by checking like average line length in your document. Like if it's like super short, it means you very likely have list. So heuristic filters are more or less like rules that you devise based on the surface level of the document. And for FineWeb 1, we employed quite a lot of them. So some examples of the heuristic filters are, for example, repetition filter, which will check if the documents contain too many repeated words. So if like half of the words is just literally like one word, I mean, it's probably not very good document. Or the other ones are, for example, punctuation filter, where the idea is that you check how many, like what fraction of the lines end with some punctuation symbol. Punctuation symbol is, for example, dot, exclamation mark, or question mark, because it kind of means it's like more nice and natural text, not just some bad quality text. Yeah. So this is this is the description of the heuristic filters, and the issue is again that we had like nice thresholds because most of these heuristic filters depends on the threshold. For example, for line punctuation, you have to decide what fraction of the lines are still ending with punctuation, are still okay, and you want to keep this document, and what fraction is like not, and you want to remove this document. And these thresholds are very, very language independent. For example, other example is the average word length. Like for English, your average word length will be like 5, but for Chinese, they just have like 1 symbol per word, more or less. So it's like very, very different values. So you just can't use your thresholds for English. You really have to adapt. And so this is one example of the problem. So this is distribution, cumulative distribution of the line punctuation, not cumulative, distribution of the line punctuation ratio. So this means that like almost no lines actually for Thai ended with punctuation in our documents, which is very easy to explain. And the reason is like Thai has like no punctuation. They don't use punctuation to end sentences. And so if we did not adapt for this kind of filter, we would remove all the Thai data we have because we would just throw them out because there was never lines ending with punctuation. And so we, as I said, we kind of had to take this threshold that we had for English, and we had to find new thresholds that we would use for the other languages. Of course, one way would be just like employ like thousands of people and kind of tell them to give us a good, reasonable thresholds they would use, but it was quite expensive to do, and again, we don't trust the humans that much on these tasks. So we decided to do this like more programmatically, I would say. And so we devised 4 adaptation techniques. So one of them was, for example, quantiles. So what we would do is that we would check for English how much data we removed, and then we would find a threshold so that for this concrete language, we would remove the same amount of data. So if for English, we would have threshold for the long punctuation, for example, 0.3, and it would and for English, it would remove 20% of the data. We would then, for let's say Armenian, we would then use the threshold that would again remove this 20% of the data. So this was one way to kind of adapt this. Other ways was using mean and STDF of the distribution of the property. So before you could have seen this distribution. So for each you can kind of take mean and STD of this distribution, and then we can use and then we can like calculate like what's the mean minus how many STDs to get the English threshold, and then we use this many STDs for other languages as well. So this was some of our like adaptation techniques we tried. And the important part is like, where do we like compute this distribution, as we can see here. And so what we decided to do is to try 2 kinds of distribution. One is the high quality data, which is Wikipedia, or stuff that is in Glotlit training corpus. This is mostly Bible, so it's more like Wikipedia plus Bible. Or just use like the very dirty data we had at this point and compute the distribution on that. Yeah. And so once we kind of found all these adaptations on all of these, on all our 9 languages, we then use these thresholds to kind of, to filter out our data set and again measure the performance. And one more important thing is that like we, in total, I think we have like 15, maybe like 15 heuristic filters, so more or less like 15 thresholds to use. And if we were to run like one experiment for every single filter, it would just be unmanageable amount. So we kind of grouped this filter into like 3 groups. So one group is the FineWeb quality filters. These are filters that we introduced for our first FineWeb. There is Gopher quality filters, which are filters that were introduced for a data set made by Google, I think, quite long ago. And the last one is Gopher repetition filters, which are all the filters that are about repetition. So for example, the like fraction of the repeated words in the document. So these are all in this Gopher repetition bucket. And then for each of these buckets, sorry? Yeah, I will explain now. So like for each of these rule filtering buckets, we run one experiment for each language we had. So So for example, this mean STD on CC means that that like when we use this type of adaptation, which is the mean minus number of STDs that the threshold was in English, and yeah, so this like these groups, the filter groups are the adaptations, and so then we took all the 9 languages, applied these filters based on these adaptation values, and we again trained the models for each language, and then we measured the performance using this adaptation technique, which in this case was mean STD. And as you can see, it's kind of very small numbers because, as said, we have 9 languages and we have to somehow aggregate their total score. So what we did is we used like a rank average score, which yeah. So this is like the rank average score for this group filter. And so in total, I think we run about 3 times 2 times 10, is it 48? Like 40 experiments just to get this table. And based on the best results for each group, so best adaptation methods for each group, we decided to go ahead with it. So for the FineWeb quality filters, we found that the best adaptation is something we call 10-tail, which is literally the dumbest adaptation technique, where we don't even consider the English threshold, and we just always remove like the 10% of the lowest data for this kind of filter. So this was the FineWeb quality filter. Then for the Gopher quality filter, we use the quantile, which is the adaptation where we see how much the English remove, and then in all the other languages, we remove the same amount of the data. And for the repetitions, we found that the best was the mean minus how many STDs we get the threshold in English. And one more thing I didn't mention or like explain is that like what is the CC and Wiki? And actually I said that we computed these adjusted thresholds on the 2 reference dataset. One was Wikipedia and one was Common Crawl. So I hope this is kind of clear. Yeah. And so one more thing, aside from these numerical thresholds, we kind of had to adapt were the stop words, where the stop words is literally like your most common words in your language. And so what we did is that we literally went by the definition and go on Wikipedia, and there we found the most frequent words for each language, and we took like 6, and we more or less, took like 6, or all the stop words that were like present in at least, I think, 1% of the document. So there was this kind of 2 condition based on which we choose. And this worked very well, but for some languages, we got like very weird results. So for example, I'm not actually sure how these languages are called, but for DAC Latin, that's like, I think, Indic language, if I'm not mistaken, written in Latin. We pretty much got the same stop words as you would get in the English. And we were like quite surprised because it makes no sense. There should be like very different words. Like it's definitely not the stop words you would use for this language. And what we found was that because we were using Wikipedia to source these stop words, many of the Wikipedia pages in certain languages are literally copied from the English Wikipedia and just put it to the subsection for this language. So this is quite problematic. And the second very problematic thing, I'm not sure if we can see it here, probably not. But the second issue is that every Wikipedia page can contain references. And sometimes like this whole references section can be written in English because again, they just copied the references section and put it into this language bucket. So it was very important to just go over all these stop words and kind of see if there is not something super weird or wrong and kind of post-fix it. And so, as I said, this is the most important step because, as you can see, we by far got the highest kind of gains, especially, for example, for French. You can see like a huge jump in our aggregated score performance. And yeah, so this was like super important step. And now the last thing, which we kind of introduced for FineWeb 2, we never did this for FineWeb 1, but it's like very motivated by what happened in the FineWeb 1. So previously we talked about the deduplication step, right? And in FineWeb 1, we also did deduplication, but we did not do it like globally. And what I mean by globally? So the common crawl, they released they like dumps more or less like every week, but you can just group them into no, they pretty much like release stuff they release a crawl every, let's say, like 6 weeks. And so what we did for FineWeb 1 is that we did not deduplicate we did not deduplicate across all of these dumps, but we deduplicated only in each of these dumps. And what was very surprising to us is that when we deduplicated inside of these dumps only, which means we introduced a lot of duplicates in the final data set because we did not do it globally, the performance of the data set was way better than when we did this global deduplication. And we were like very surprised by this result because again, if you don't deduplicate globally, you inherently will have the duplicates inside your data set. And so one possible explanation was that when we are deduplicating globally, every single like duplicate group, like the cluster of the duplicates, we only retain one sample, right? We just take all the groups and we just sample one random sample. But if we do it per dump, again, we can kind of have some duplicates. But because we have like very small amount of dumps, let's say 100, in the result, it kind of means that when we are deduplicating independently, we kind of upsample the very small like cluster sizes, very small clusters, and heavily dump sample these like huge clusters of duplicates, which are usually like TOS, cookies, and these kind of stuffs. So when we are doing this independently, we kind of upsample the small clusters, which we thought is maybe some kind of proxy for data quality, and so we decided to inspect. And so what we did is that we plotted the cluster sizes that we had for French, I think this is French. And so on the x-axis we have the cluster sizes, and on y-axis we have the removal rate for this cluster size. So for example, there you can see there is like cluster size 20, of 25 documents, and you can see the removal rate is like very small. But for these like huge cluster sizes, like let's say 200 or like even more, this is like the long tail, where these clusters are like very big, we have like very high removal rate. And this removal rate is like computed from the heuristic filters that we applied in the previous step. So this kind of means that the huge cluster sizes contained documents that we removed a lot, which means they contain like a lot of documents that we consider are very bad, while the small cluster sizes at the start like don't have such high removals. So it means that compared to these huge clusters, they actually contain like more high quality data. What's a bit also surprising is that it's not like linear from the start. So like the best bucket would be, the cluster size would be just of the size 1, but it more like resembles the U shape. So the optimal kind of cluster size is a bit dependent on language. And so with this knowledge, not too much. And so with this, and so since we kind of found it, what we decided to try is that for the lowest point, so for the lowest removal rate, we're gonna upsample by like 10 times, and for the highest removal rate, we will actually do no upsampling whatsoever. So we will just keep the same data we have, but for the cluster size of 25, we will like heavily upsample. So every sample from the document, every sample that has 25 duplicates will be duplicated 25 times. And this very surprisingly helped a lot because we like upsample the documents that are like higher quality compared to the others. And as you can see, like we got very nice boost across all these languages. So this was like very, very surprising finding to us because up until this point, like everybody really thought that you just want to globally deduplicate and you want like more or less no duplicates in your dataset. But this very much proves that it's okay to have duplicates, but you want to duplicate the high quality samples, not your bad quality samples. And so this is more or less it. This is how we build the FineWeb 2. This is like the final table that kind of compares to other multilingual data sets. And what we also did to kind of prove that we did not just over-optimize for our 9 languages is that we took other 5 languages we have never seen during the training, and we just evaluated the performance on these 5 languages. And we are the best on 1, 2, 3, on 3 out of 5. So not bad, considering we are comparing to all the other data sets. And if you consider all the languages we have here, we are the best in 9 out of 14. So based on this metric, I would say we are the best multilingual data set. And we are glad that there are many people that kind of trust our quality of our data sets. So there are already models built on top of FineWeb 2. So one with small LM3, which we released recently, I think 2 months ago. One is GLM, which is like a very big model made by a Chinese company. And one is a recently released model by NVIDIA, which is also inherently multilingual because they trained on our data set. This is not super readable, but we really strive to make all stuff we do open. So for us, it just doesn't mean opening the final artifact, but we really want not only like the description, what and why we did, but we also want to release the filtering pipeline so you can actually in theory just run the processing yourself. And yeah, this is it. I'm not sure if there is like some slide sharing, but if you want to see all the artifacts we created with the datasets, you can kind of click through the URLs. Yeah, so that's it. I hope we finish in time. And now I think it's time for questions. One more thing is that we recently released another dataset made out of the PDFs. So if you have any questions, not just about FineWeb 2, feel free to ask about that as well.
Can you please go back to this?
Sure. Which one?
The way you decided.
This? This?
This one.
Uh-huh.
What is the y-axis here?
So y-axis is how much the heuristics filter we used removed. So if it, so if it removed a lot of documents in this cluster size, it means that like a lot of documents of this cluster size are like very, very bad.
Very bad.
Yeah, because we removed a lot of them.
But not duplicate.
No. This is purely about the quality kind of, yeah. So if we removed a lot of them, it means that a lot of the documents that have this much duplicates are like worse quality. Does it make sense?
So you say that there is a correlation, okay.
Yeah, there's
this part that the larger cluster sizes
contain bad documents. Not
something to be removed more often.
exactly.
In a way.
Yeah, and thus you don't want to upsample these documents. You want to upsample your high quality documents, which are in the all the documents that have like 25 duplicates.
But if you already removed the bad ones, doesn't it mean that this cluster, the remainder of the cluster is high quality?
So like the heuristic filters remove stuff, but they don't remove all the bad documents. So there are still like a lot of documents that are kept, and like clearly the cluster size is like very good proxy actually for the document quality.
You discovered that
If there's like a huge cluster of documents that are very, very much the same, which for example are all those TOS notices or those cookies and all those stuff, there will be huge clusters of these because all of these documents are the same. We don't want to upsample this. We want to upsample the documents that have like 25 duplicates because empirically these seem to have contain like more kind of quality content, which clearly boosts the performance.
the
Clusters will be TOS stuff, and these I'm not sure why the clusters that have like 1 or 0 documents are bad. I'm not sure about that, but probably the stuff was not that important, so that's why they did not crawl that thing again, and so that's why probably it's also making stuff worse.
How much did you upsample?
Yeah, it doesn't say here, but we found the cluster size that had like the lowest removal rate, so the best quality documents, and we upsampled it 20 times. And then we took the cluster size that had the worst quality documents, and then do like simple linear interpolation. So I think, for example, the cluster size, I don't know, 75, we would upsample like 10 times more or less.
It means that on average you go for, I don't know, a couple of epochs or 3, 4, no, even more, 10 epochs.
Yeah, it's, yeah, I think so. Yeah.
The number of clusters of this cluster size, right?
Yeah, that's very much true. Yeah, that's very much true. This is a cluster size. It's not like linear. Like you will have very likely a lot of cluster sizes of size 200 and not that much of size 25. Yeah, it's not very easy to kind of tell how many repetitions we have.
How do you cluster?
Cluster? It's from the min hash. So it's like similar documents using min hash, which literally works the way that you take the back of words of two documents, and then you take like intersection over union of these back of words, and if it's higher, I think, than 0.8, you consider it a duplicate. It's not exactly this because we have to use the approximate method to get it running faster.
Okay, so here cluster means duplication.
Yeah, exactly.
One in the same cluster.
Yeah. It's like it's a very similar document. Like, as I said, like all the TOS where they only change the name of the company, for example.
And then I'm trying to understand how is that computation really philosophical different. So you have billions of sentences maybe.
Sentences?
To cluster, right?
Words. We separate on words. We have document, we separate on words. We get the back of words of the document, and then we compare to all the other documents, and then check intersection of the over union of these words. So the cluster is all documents that are similar transitively to each other.
But then you have to do some sort of n-squared comparison.
Yeah. But like this is like the idea behind it. There is like the min hash is like linear because you do it like smarter way, which is not like you will kind of have some false and positive. You will have some duplicates that are not duplicates, but it more or less works. Yeah.
I see. So min hash is the word that.
Yeah, min hash is the one that does that creates this cluster because it deduplicates. It gives us like it will create these clusters, and then for each of the cluster, it will sample one document. Yeah. So these clusters are made during the deduplication step.
Okay. Do we have questions?
Yes, question. How did you get that formula with minimum and maximum?
Sorry? Yeah.
You had a slide with you were calculating the score or something.
The confidence scores?
You have the minimum, maximum, and the median and standard.
Yeah, this one. This one?
How do we get with that formula?
How do we calculate what?
There is a formula with.
Yeah. So like how we decided to use these formulas? I mean, it was more or less we kind of like was thinking how we can adapt the thresholds to our new threshold. So we came up with these four.
So this was like a mistake.
Yeah. There was like we didn't fit any model. This was like, how can we take a number and then adapt using properties of the distribution of this metric to the other ones? And we kind of came up with the four like ideas we could use, and then we literally tried all of them and found.
From where it came initially?
Sorry?
You're saying you are extending the version from English?
Yes. Yeah. How the English? So those are handmade. All those thresholds are handmade. There's like no smarter way. It's just like people look at the documents and they're like, yeah. So like if there is like more than 12% of the lines that don't end with punctuation, it's probably not super good document. So it's all handmade.
Thank you for the talk. I think you mentioned at the beginning that you run experiments in 1.5
Uh-huh. Yeah.
30 billion tokens.
Yeah. So we run 1.4B model for 30 billion tokens.
Yeah, so like one chinchilla trade.
Yeah, exactly. It's like chinchilla optimal.
So given that current models overly overtrain now, and so there's a huge research in optimizers, for example, that runs on 4 chinchillas, and the data set is also really huge, right? Did you compare, or do you have any results on whether it's beneficial to run more chinchilla?
Yeah. So I mean, like every ablation we kind of did throughout the time was on 30B. And then all these are actually from 100B. We kind of wanted to have like more confidence. But even though, even that, like we never trained, let's say 70B on 1 trillion because simply we don't have enough compute to run it for 9 times 4, which would be quite a lot of experiments to run. So so the best thing we ran was the 1.4B on 100 billion tokens, which are all these. And also, like all of these data sets, models, are actually built on FineWeb 2, and I think the GLM one is actually quite good, and small m is kind of okay as well. So it's kind of like proof that it scales to bigger sizes as well, even though we don't have concrete ablations for that.
Thank you.
Yeah.
More questions? So how much compute you spent on this?
I don't know. I honestly have no idea. I think it's gonna be like 100,000-ish, maybe 200,000-ish GPU hours. Yeah.
I see.
H100 GPU hours.
I was wondering, what does it mean exactly deduplication? Because you mentioned that we have clusters which contains duplicates, and we just randomly choose one of them and delete the rest.
Yeah. So we randomly sample one of the samples in the cluster. So it's like one representative, and it's chosen randomly based of all the duplicates. But this is a very good point. I think like there is also like a lot of study that could be made on how we should actually choose these like representatives. And maybe when we're doing the repetitions, we don't have to just run on the representatives. We could every repetition we could like resample from the cluster sizes. Yeah, I think that's actually a very nice thing we could do as well.
And you are training with one epoch, right?
Here everything is run in one epoch. It's like, because we chose the languages so that actually we also have enough data for one epoch. Because previously, we are done.
It's okay.
Yeah, so like previously we also had like one language that was like super small resource, and we only had, I think, 2 or 4 billion of tokens. And there, like the objective of the filtering changes a lot because you are in like data constrained manner. So like you really have to kind of account like whether you want to remove and introduce more repetition or not. And we didn't want to deal with this confounding factor.
But when you say one epoch, you mean this oversampling included, right? In a way.
Like every single of these is one epoch. So it's like we take the globally deduplicated thing and just train on that. Like if we have, for some languages, of course, we have way more than 30 billions. So we somewhat sample and use random sample, which can introduce a bit noise. But we kind of accounted for this, and that's why you have these wiggles, which are like worse than the best performance that you should get using a random sample of our data.